Paging Dr. Dennis. Paging Dr. Dennis.
Dr. Dennis, we need you now. We're off the air. Transmitters are down.
Hello, I'm Dr. Dennis, the engineer of this radio station. We are currently experiencing some technical difficulties. I will try to get you back up on your regularly scheduled programming as soon as possible. In the meantime, in this studio, I have a very special guest, all the way from MSU. He's a real-life theoretical physicist. Ladies and gentlemen, it's Nicolas Yunes! All right, Nico Yunes. Hey, welcome back in our studios.
Thank you. How are you?
Pretty good. Hey.
How have you been?
Oh, I've been pretty good.
I hear you're having difficulties on stairs.
I am. The electrons in the file server are spinning backwards. You think you can help me with that?
We'll have to look at that. I don't know what that means and how we can solve the problem of backward moving electrons. We call those positrons.
So what's physics?
Physics is a way to try to understand nature. It's a way to systematically organize all of our knowledge about nature and try to predict what's going to happen in the future given what we have observed in the past. It's like, for example, trying to understand how the sun works. And why would you care about how the sun works? Because the sun, turns out, explodes every now and then. We call those mini explosions solar flares. And if you've ever seen a movie of the sun taken by some fancy telescopes that we have up in space, you'll see these like rings of fire, right, that come out and then they close back in, and sometimes they just escape. We try to think about how the sun works, so we can then predict how the sun is going to behave in the future and how these explosions are going to affect our satellites and space weather. And then we can check, right? We can predict that in 28 days there will be another solar flare. It's a forecast. It's like a weather forecast. So physics is like forecasting the outcome of experiments by trying to understand what we've observed before and why what we've observed before happens.
So
that involves everything. It's not just but everything that's nature-based. We're not talking about explaining the behavior of people because that's way too complicated.
No, we don't want to do that.
No. We want to understand, what happens when particles collide. What happens when stars explode. We want to understand
what happens in a black hole.
What happens in a black hole? What happens when you take a clock, two clocks that tick at the same time, like at the same rate, that are synchronized on Earth, and you take one and you put it up in a satellite. What happens? Does it continue to tick at the same rate or not? Spoiler alert, it doesn't. It doesn't, right? And this matters because understanding how clocks tick allows us to triangulate signals. It allows for the functioning of the global positioning system, that thing, GPS, that's inside of your phone. Super useful, right? But, you would not be able to make GPS work if you do not understand how clocks tick in a gravitational field on Earth versus in space. What happens when you fall into a black hole?
We're talking about general relativity now.
General relativity,
well,
Einstein's beautiful theory, yeah.
You know what tools do you use to figure out physics? You use thought experiments?
We do, yeah. We use every tool we have
that
we can think of, right? So we write computer programs, and this is not just like we go and we purchase software from somebody else. We go and we write our own programs because most of the time those programs don't exist, right? And then we make them publicly available, of course, so that other people can use them. We write computer code, and then we launch this code in clusters of supercomputers. Imagine like the most powerful computers that we've created or that we create, and then we interlace them all together and we run them all at the same time. Then we also derive and solve things with complicated mathematics on a board or on a whiteboard or on a paper. And sometimes, guess what? The mathematics doesn't exist. Sometimes you have to come up with your own mathematics. You have to invent new tools.
Do you use your imagination?
You have to use all the time your imagination. You have to create new things because if the tools existed to solve a problem, chances are somebody's already solved it, right? So most of the time, we have to invent new things. We have to invent new computer code. We have to invent new mathematics. We have to imagine what would happen if I throw Dennis into a black hole, what would happen if Dennis is right in between the collision of two neutron stars? What would happen if I could measure all these things? And what implications would that have on Earth? Of course, when two black holes collide or neutron stars collide, this happens very, very far away from Earth. So as far as we're concerned, nothing really happens. But understanding the physics of the collision of these objects then has implications for how physics also works on Earth. It has implications about how clocks tick when they're traveling at a certain velocity or when they're outside of a gravitational field. So this knowledge we acquire by observing the most extreme collisions, we can then use in applications on Earth. Needless to say, a lot of times to actually observe these collisions, we have to build machines that don't exist. We have to create this new technology that's not out there yet, but we need to build it. We need to come up with new ways to measure. And that ends up having lots of applications in everyday life.
What are you measuring?
We're measuring, for example, the latest observation of gravitational waves. So you probably know, and your listeners probably know, that the Nobel Prize this year was given for the discovery of gravitational waves. Yay! That's right. So,
and it was on my birthday last year.
Was it on your birthday?
That's when LIGO announced it, February 11th.
That's fantastic.
Yep.
Happy birthday to you and to the gravitational wave community, right? So LIGO is this machine, right? It's two machines, one in Washington State in a place called the Tri-Cities, and another one in Hanford, and another one in Livingston, Louisiana. These machines are gigantic. These are like, each machine consists of two tubes. The size, the tubes are cylinders. Okay, they're the radius or the size of a human, if you want. But the length of the tube is 3 miles long. It's really, really big, and it's two of them, and they intersect. They form this like L shape, if you want, or two sides of a square. Yeah. And then what we do is we shoot lasers, super powerful lasers, into these tubes, and we bounce the laser beams at the end of the tubes, and we let the beams recombine. And what are we measuring? We're measuring the amount of time it takes for this light to get from one end of the tube and back again. And that amount of time, you would think, is always fixed, right? Like I launch a photon, and it goes to one end of the tube, it bounces, it comes back, and I then launch the next photon, and the amount of time it takes for that next photon to come back should be the same as the amount of time it took the first photon, and so on and so forth, right? But that's not true. Photons can slow down. What? Yes, what? Photons can slow down because space and time are not fixed. That's what Einstein taught us. Space and time are flexible. They're like membranes. They're like silly putty. You can distort them. You can stretch them. You can compress them depending on how strong gravity is. And so what happens is these black holes collide millions of light years away from us, and they produce these vibrations in gravity that then travel these millions of light years until they hit Earth. And then when they hit Earth, they slow time down a little bit, and then they don't, and then they slow it down a little bit more, and then they don't. There's these oscillations in the time of arrival of the photons, and so you have to measure this time difference very accurately. Another way of thinking about it is that the gravitational waves really are not changing time, but they're changing space. The length, the distance between the ends of the tubes is getting compressed and stretched and compressed and stretched. Wow. So the amount of time it takes light to get back to where it came from, it's going to change as this tube, right, grows and shrinks and grows and shrinks. And so by measuring this distance very, very precisely.
How big is that distance?
Oh, the distance is incredibly small. So you're talking about a light particle, a photon, traveling 3 miles, right?
Right.
And the change in the distance is 1 part in 1,000 the size of a proton.
Wow.
That's ridiculous. That's like measuring the width of a human hair that is placed in Proxima Centauri, okay, from Earth, okay? I'm looking at Proxima Centauri, that the nearest star to Earth is light years away, okay? Light years meaning very far away. It would take years for somebody traveling at the speed of light to get to this star, okay? And that's the closest star, apart from the sun, obviously, that is to the solar system. And, this change in distance is like measuring the width of a human hair in Proxima Centauri. It's crazy. It's unbelievable. And we've measured it.
You measured
it? I haven't.
Last time you talked,
I don't measure things.
Well, last time we talked, they were getting close.
Yes. And this started way before I even started doing physics. This had started in the 70s with this crazy idea of Ray Weiss and Kip Thorne and Ron Driver and others to say, well, Einstein predicts that these vibrations in gravity should be real, so how can we measure them? So they started thinking, well, we need these very long tubes, but the technology doesn't exist. Oh, we'd better bring some engineers and some industry people that can build us really precise tubes and really precise mirrors to bounce this light
They
off.
have to be the most polished thing in the world,
In the world, the most stable lasers, because if the laser, the thing that's shooting the light, has fluctuations, then you could get confused.
You figure a truck going by could set it off, right?
Exactly.
So is that why we have multiple ones of these?
Yeah, so that you can have coincidence, so that you can't be fooled into believing that you detected a gravitational wave when in reality it was just a plane that was going right over the instrument, right? I mean, that probability of these things happening exactly at the same time with exactly the same pattern in two places that are so far away on Earth, right? Washington State and Louisiana, these are very far away. In fact, light takes about 8 seconds, or no, less than that, to get from one to the other. So, so the probability of this happening at the same time, that would be insane. That would be crazy. So
they
that's
actually measured it. And
they measured it.
So this is what it sounds like.
Yes. And it's like a motorcycle, right? It's like...
Here, let's hear it again.
Oh, you mentioned the actual sound? Okay.
Oh, wow, this is cool.
It's pretty awesome. Yeah, it's pretty awesome. It's almost like the universe has a symphony that we have not been able to hear until now. Of course, it's not sound, right? What you're hearing is not sound waves. These are just vibrations in gravity that, because they look like a sine wave, we can just play with a speaker. We just make the membrane of the speaker vibrate at the same frequency as this sound wave that I gave you, and that's what you're hearing. It's like converting the waves of gravity into waves of sound, but it provides amazing information, just like sound does. And what kind of information? Like, if you're blind but you hear sound, you can localize things, right? You can say, oh, that sound came from over there or from over there. So when we hear these gravitational waves, we can tell where they're coming from. We can triangulate, and we can say, oh, something created a huge explosion in gravity right over there.
In that direction. Wow.
And then all of the satellites on Earth can pivot and point to this point in space where we heard an explosion in gravity. And guess what? Recently, they saw something in light. All of these telescopes, that they see light, right? That's what telescopes do. They detect photons. They saw the light emitted when two neutron stars collide. These are like stars like the sun, but much, much, much more dense. Imagine you take the mass of the sun, this like superly heavy object. You have you can fit thousands of Earths inside of the sun, many thousands, in fact. Millions, one might even say. And imagine compressing all of that matter into a tiny ball, roughly the size of Bozeman.
Wow.
Like, what? That's how dense a neutron star is. And now, slam one of these objects against another one of these objects traveling at half the speed of light. What? Yeah. That's what happened. Two neutron stars of about 1.5 times the mass of our sun collided at roughly a third the speed of light, and we heard the gravitational waves that were emitted during this collision.
That's so cool.
And then we told all the astronomers, look over there, something just amazing has happened. And everyone looked, and they started seeing all this light that was generated by this collision of neutron stars. They saw X-rays, they saw radio waves, they saw things in the infrared. Every telescope on Earth essentially pointed at this point in the sky. It was really a collaborative human experience because, these telescopes are not just in the U.S., right? They're everywhere.
That's exciting.
It was pretty awesome. Yeah.
So, hey, I got to go downstairs real quick and check on my file servers. So we're going to take a little commercial break here. And when we come back, I got a question for you. Do you like the Big Bang Theory show?
Oh, yeah, I love it. I mean, I take it with a grain of salt, but it's fun, of course, yeah.
So when we come back, I want to talk about the Big Bang.
Oh, I thought you had some of the actors here that we could talk to.
No,
oh, next time.
Okay, we'll be right back.